Well, hello again, calculus fans. Hopefully you guys are doing well, and we'd like to welcome you to the third week of our virtual class. Before I get started with other things, I want to mention I did get emails from Abby and Meredith saying that you guys and also Garrett were interested in doing the National Quiz Bowl virtually this summer, and I would love to have you. I think it could be very fun. Reese, if you're interested in doing that, we would love to have you also. And Eric has also told me that he would like to be part of that. If any of you have contact with Alex, like if you have his number in your phone or whatever, if you could pass that on to him and get him to commit, I really think he should do this, especially now that it's just at Garrigan. There's no reason why he can't. But one way or another, we'll try and work things out and get that happening this summer. So you might have noticed that the picture you're looking at is looking out a window. In fact, you're looking out my front window with the view I have most of the day when I'm sitting here at my computer. And in that window, you'll notice there's a glass starfish, which I happened to get years ago at the Boston Museum of Fine Arts. Right next to that is a stained glass object that a student made for me probably about 25 years ago. And I really like that. I also have it in the window, and I decided to put that in the picture today because it involves a whole bunch of geometric shapes. And in fact, a lot of the problems we're going to look at today are geometry problems. The topic we are going to be doing today deals with optimization. And in fact, we're going to be looking at optimization for a while. We're going to start by looking at what amount to geometry problems, and then next week we'll be taking a look at some business problems, which honestly are easier than a lot of the geometry ones. This picture, which I stole after doing an image search on Google, came from a professor who, just like me, was creating a PowerPoint to teach a class over computer that had suddenly transitioned from being live. That's happening at just about every college in the country this spring, as well as at a lot of high schools. And so, yeah, this happened to be somebody that was at Indiana University and making that same kind of transition that you are. First of all, show you two typical geometry optimization problems. Then we're going to go through the steps that you use to solve them, and then we're going to go back and solve those two problems. You'll be doing a worksheet that has a bunch of optimization problems on it. If this were a normal year, what you would probably do after that is you would be making up some problems of your own, kind of like you did back in trig class, and sharing those with each other. Unfortunately, that probably won't happen this year, so you don't get to be quite as creative as you would otherwise, but you will get to solve some problems. So our first problem here, it says a homeowner wants to plant a rectangular garden along one side of a house. When I first took calculus, I remember I don't know how many problems that dealt with rectangular gardens. And it turns out it's almost a cliche in calculus. You could Google the phrase rectangular garden and come up with hundreds of calculus problems like these. They always have a little bit of a twist to them, and this one says that there's a picket fence on three sides, and we're supposed to find the dimensions of the largest garden that could be enclosed using 40 feet of fence. Now, the reason there's always some sort of a twist is that if you didn't have like the fourth side that was up against the house, what you would end up with is four pieces of fence. And if all of those were equal, the optimum area would always end up coming from a square. So they always have something like this that makes it not be a square. And here we're trying to figure out what would these optimal dimensions be. And here's a similar problem, but there is one major difference to it. It says the manager of a department store wants to build a 600 square foot rectangular enclosure on the store's parking lot in order to display some equipment. 3 sides of the enclosure will be built with redwood fencing at a cost of $7 per running foot. The fourth side will be built of cement blocks at a cost of $14 per running foot. And again, we're supposed to find dimensions, but this time we want to minimize the cost of the building materials. Now, I will tell you, in the real world, you'd almost certainly find that the redwood fence would cost more than the cement blocks, but we're going to go with what it tells us here. There's basically 5 steps that you need to do every time you want to solve an optimization problem. And that's true on the geometry problems. It'll also be true on the business problems. And if you went into like Calculus 2, you'll find variations that get more complicated, but they still boil down to the exact same 5 steps. The first step is that you come up with what we call an objective function. The objective function is the object of the problem. It's what you're trying to do. And in particular, it's the thing that you want to maximize or minimize. In that first problem with the rectangular garden, we wanted to maximize the area of the garden. And in the second one, where you were enclosing an area in the parking lot, they wanted to minimize the cost of construction. Whatever you want to maximize or minimize, that's your objective. The objective function is usually pretty easy to come up with. It's either some formula you know from geometry, like the area of a rectangle is length times width, or it's something that you put together with information that's given in the problem, which is what we'll do on that cost one. But again, whatever you want to maximize or minimize, that's the objective. The second step is what we call the constraint equation. And the constraint sets limits on how big the numbers that go into the objective can be. If I wanted to maximize the area of a rectangle and I didn't tell you anything else, I just keep making that rectangle bigger and bigger and bigger until I had covered the entire Earth with a rectangle. Assuming you had like a flat Earth to cover it with. So instead, there's always going to be something in the problem that sets a limit so you can't just keep on going forever. Sometimes it tells you you have a certain amount of material you can use, or there's a certain cost you have to have, or there's a certain area that you have to build, like we did in the second problem. Whatever it is that sets a limit, that's going to end up being the constraint. And you want to look for numbers. And again, they sometimes do involve geometry formulas, but it's always where the numbers come in the problem that matter with constraint. So we have our objective and we have our constraint. The third step is to solve the constraint for one variable in terms of the other. In both of the problems we're going to do today, the variables basically are length and width, although if you read them closely, they actually use a different variable than L. And basically what I want to do is make the equation either say L equals something in terms of W or W equals something in terms of L. It doesn't matter which way you do it, although sometimes one of them's easier to come up with than the other, but you just want to write one variable in terms of the other. The reason why we got one variable in terms of the other leads into the next step, step 4. And it tells you here that what we do is we substitute into the objective so that our goal is to have a function that just has one variable. I might have started with something like area equals length times width, and now what I'm going to do is change the width into something that's in terms of length so that all that's in my problem is just length. I only have one variable instead of 2. So you substitute, so you just have one variable. The key to the whole problem is step 5, the last of the steps. And what it tells you here is to set the derivative equal to 0 and solve. The whole reason why you set the derivative equal to 0 is remember that when the derivative is 0, you always are at a maximum or a minimum problem. Last week when you were doing those questions about when is the ball at its highest point, you set the derivative equal to 0. Well, the same thing is going to be true if I want to find out how am I going to get the maximum area. I set the derivative equal to 0. Or if I want to find the minimum cost, I do derivative equals 0. So I set the derivative equal to 0, and then I'm going to solve it to figure out what I've got. Now I have in parentheses after that you want to then go back and make sure that you've actually answered the questions in the problem. Sometimes they'll ask more than one question, and you need to make sure that you have actually covered everything. If we were actually at school doing these problems, I would have started by passing out a worksheet that had a bunch of them on it, and then we would have gone back and done a couple of the problems as examples. That's basically exactly what's happening here. You're going to be doing a worksheet later on, and these are two problems that we're going to use as examples with those. So again, our first problem, it says a homeowner wants to plant a rectangular garden along one side of the house with a picket fence on the other 3 sides of the garden. Find the dimensions of the largest garden that can be enclosed using 40 feet of fencing. And the first step we've got to do is to find an objective function, which is the thing we want to maximize or minimize. Well, the problem says we need to find the dimensions of the largest garden. So what it's asking us to do is to maximize the area of that garden. We've got to find the largest possible area, and that would be the area of a rectangle. Now, if you look at the picture, they have the sides here labeled as X and W instead of L and W. I'm pretty sure they did that because if you use an L, it can look an awful lot like a 1 when you're writing stuff out, and the X is just a different variable then. So that's why my objective function is going to be the area equals X times W. Again, just length times width, that's my objective. Step 2 is to find the constraint, the thing that sets limits on this. And here, it's the fact that I only have 40 feet of fence. I can't use more than 40 feet. Well, if you look at the picture, the things I'm actually enclosing are 1W. I've got one long side here, and then 2 of the X's, 2 of the shorter side that we have on this. And that's why my constraint is going to be 2x plus w equals 40. Again, it's just what I have to make, put them together, and I've got 40 feet of fence. Now, I will tell you that it's possible that some point in the future you could run across a different instructor that would make you write that as 2x plus w is less than or equal to 40. And that's because theoretically you could use less than 40 feet. You can't use any more than that, but you could theoretically use less. The fact is, though, that you're not going to find the maximum area if you use less. It's only going to happen if you use up all of your fencing that you have available. And that's why equal really is the most sensible thing to write there. So we've got our objective, which is just the area is x times w. We had our constraint, which says 2x plus w equals 40. And now step 3 says we're supposed to solve the constraint for one variable in terms of the other. And I put, when I originally wrote this, solve it for L or W. Here it would either be X or W. I always choose to solve for whichever one is going to be easiest to get by itself. In this case, it's easiest to write W equals 40 minus 2x. If I really wanted to, I could have said x equals 40 minus w all over 2, but that just makes a much harder expression, and there's no reason to make things more complicated than they are. So w equals 40 minus 2x. Step 4 said to substitute into the objective so that we get a function that just has one variable. Well, our objective said a equals x times w, and we just figured out that w equals 40 minus 2x. So what I'm going to do is I'll go back to the objective, and instead of w, we'll change that to 40 minus 2x. So when you do that, you get x times 40 minus 2x. You could leave it at that, but it honestly makes it easier if you go ahead and just distribute out the parentheses and make it say 40x minus 2x squared. The reason why it makes it easier to simplify is in the next step we're going to do the derivative, and it's way easier to do the derivative of that than to think about stuff like product rule and try and do the derivative of the one above. So yeah, multiply it out, get 40x minus 2x squared, and that's going to end up being our substitution. And again, the single most important step is to do the derivative equals 0. Well, the derivative of 40x minus 2x squared is 40 minus 4x. And so I set that equal to 0. Sometimes I'll have people that say, what happened to the a? Well, if I wanted to, I could have put a prime equals 40 minus 4x, and then set that equal to 0. Really, you can just get rid of the a, and just take the derivative of the main part equals 0. Now I have to solve that, so I got stuff on opposite sides, 40 equals 4x, and then divided by 4, and we get an answer of x equals 10. When I put this up originally, I had a line there that said, make sure you've answered the questions in the problem. And so if I go back and look at the problem, it says find the dimensions of the largest garden. And the key word there is dimensions, plural. That means I need to know both the width and the length. And so far, I figured out that one of the dimensions is 10. I need to find both of those, though. So what I'm going to do is take that 10, go back to the formula I had earlier to find w, and take 40 minus 2 times 10. And it's not too hard to figure out that we get 20 for the answer, so we end up with a 10 by 20 foot garden. Now, it's always worth double checking to make sure your answer makes sense. We're supposed to have w is 20 and x is 10, and yeah, that certainly does make sense in the context of this problem. I do want to warn you, though, that the pictures are not always drawn accurately on problems like this, so it sometimes will happen that your shorter side may look longer in the picture, and that's okay. Here's the other problem that I had earlier, where it says the manager of a department store wants to build a 600 square foot rectangular enclosure on the store's parking lot in order to display some equipment. 3 sides of the enclosure will be built from redwood fencing at a cost of $7 per running foot, and the 4th side will be built of cement blocks at a cost of $14 per running foot. Find the dimensions of the enclosure that will minimize the cost of materials. And again, the first step is to find the objective function. We need to figure out what we want to maximize or minimize. This time, we want to minimize the cost of our building materials. And in my picture, again, they've labeled things with X and Y. When you look at this picture, I've got to do all 4 sides of this, but 3 of them are of the cheap material and 1 of them is of the more expensive material. So like both of the Y's are going to end up costing $7 a foot. And for the X's, one of the sides will cost 7 and one of them will cost 14. And that's where I get this formula that the cost is going to end up being 7x to build the top of that picture, 7y to build the left side, 7y to build the right side, and 14x to build the bottom. Each of those is just how much the side costs per foot times the number of feet. When you combine like terms, we end up with 21x plus 14y. So next we've got to find the constraint equation. And the constraint here, the thing that sets a limit on it, is the fact that it has to be a 600 square foot lot. So I need to have the length times the width, x times y, equals 600. We solve for one variable in terms of the other. The way I do that here is just to divide both sides by x. I get y equals 600 over x. If I wanted to, I could have said x equals 600 over y. Again, it really makes no difference which way you do that. Then we have to go back to the objective and substitute. So our objective again said 21x plus 14y. Now what I've got to do is change the y to 600 over x. And so when I do that, it's going to say 21x plus 8400 over x. And just like before, I can make my life simpler if I get the equation as easy as it can possibly be before I take the derivative. Here, I know that 8400 over x is the same thing as 8400 x to the negative 1. So I wrote my objective as 21x plus 8400 x to the negative 1, and that's what I'll do the derivative of in the next step. We've got to do derivative equals 0, and so I think what would be the derivative of that? And the good thing about pretty much all of these optimization problems is it's comparatively easy to do derivatives. You don't really need to worry a lot about like trig functions or product, quotient, and chain rule. If you go into Calculus 2, you do start having to worry about stuff like that, but not really in the problems we're looking at now. The derivative here is going to be 21 minus 8400 x to the negative 2. It is minus because remember you're doing negative 1 times 8400. That's going to end up equaling 0. Now, of course, the problem says set it equal to 0 and solve, and the question that's probably going through everybody's mind right now is how the you-know-what do you go about solving that? So we need to think about how we could go about solving that. This kind of problem tends to happen when you do have minimize problems rather than maximize. And the key thing is I always want to get the numbers and the x's on opposite sides. So here I moved 8400 over to the right-hand side, so it would have said 21 equals 8400 x to the negative 2. But I also remembered that if I have x to the negative 2 power, that's the same thing as over x squared. So the equation I have at the top would be equivalent to 21 equals 8400 over x squared. Now what I'm doing is cross multiplying, or you could think of it as multiply by x squared on both sides. I end up with 21x squared equals 8400. And suddenly I've taken it from something that looks impossible to solve into something that's not that hard to solve. Because now I just divide by 21 and I take the square root, and it turns out that x is 20. So again, get the x's and the numbers on opposite sides, write it as a fraction, cross multiply, and then solve that. The last step, of course, is to make sure that you have actually answered the questions correctly. And once again, it tells us that we need to find the dimensions. We need both the length and the width. And so what I do is I go back to that step where I solve for one variable in terms of the other. And here we had y equals 600 over x. I take 600 over 20, and you end up getting 30 for what y has to be. So our answer is that we've got a 20 by 30 foot enclosure. Now this is one where the picture that they have illustrated there doesn't really look right, but there's a darn good reason why it doesn't. Here, x is actually the 20 and y is the 30, so the side that they drew short actually is the longer side. The reason why that happens is that x is the side that's expensive to build, and you want to make the side that's expensive as short as you can get by with, and so that's why it ends up being a shorter side than the y does. So, here we do end up with a 20 by 30 enclosure, and that is going to end up being our answer. And so your basic steps again, first you do want to find the objective, the thing you're maximizing or minimizing. Then you've come up with a constraint, whatever the numbers in your problem are, the thing that sets limits on it. You solve that constraint for one of the variables. Then you substitute that back into the objective so that you just have one variable in your function. You do the derivative equals 0 and come up with whatever the answers are. You're going to have a bunch of problems to practice that, and you probably will end up with about 2 questions that are broken down into multiple parts for your quiz at the end of the week. I haven't even thought about coming up with a quiz yet on this, but we will at some point. And what you want to do is make sure that you know those basic steps and that you can come up with the final answers on things. So do practice everything. Good luck with it. And again, I'm looking forward to seeing you guys again to do the National Quiz Bowl, but hopefully we'll see you well before that.